Okay, 7.2 is using these integrals to figure out volume. Um, you'll study, you won't necessarily use this method in the future. In the future, you'll have more powerful methods to figure out volume. So you'll have, I guess, uh, iterated integrals is what we'll probably call them to figure out your volume. But we can cheat a little bit with the Riemann sum and backdoor the answers at this point. So you want to think of integration as kind of picking up rectangles as you move along, but then here we're going to reinterpret the rectangles as kind of cross sections of disks. Right, so we want to first recall the Riemann integral in its basic form. So recall how that worked. Basically, you would have some sort of curve, and then underneath the curve, you would section it up into a bunch of little rectangles, right? So here's our curve, and then we can cut it up into all these little rectangles. Let's call the curve f of x. So on and so forth. Maybe we have a generic one right there. Okay. So we have some generic rectangle, and we can designate a point x sub I in here, such the height of this rectangle is f of x sub I. So in particular, the area of this rectangle, a sub I, would be, like I said, f of x sub I, the height, times the width of the base. And we'll presume that the width of the base is called change in x, right? So length times width, f of x sub I, times change in x. Then we could get an approximation to the total area underneath the rectangle just by adding up all these guys, right? So the area is approximately the sum of the area of the rectangles. And then if you let n go to infinity, you would kind of have the integral that we're familiar with, right? Okay, we want to reinterpret this process now where these rectangles don't necessarily, we're not going to add up areas. We're going to pretend these rectangles are the cross sections of disks. Okay, so how is this? What's going on? So now what's going on? We have the same picture. Okay, so I'm going to use the same function. Looks like this, sort of. And you know, we have some interval we care about, something from like A to B. And we have sectioned it up into a bunch of little rectangles. And then there's this generic rectangle on the inside here at x sub I. And then all the way over to these other rectangles at the end. Okay, so instead of thinking of these as rectangles, we want to think of them as cross sections. And what we're kind of doing is spinning these things. If you want to get there, get to the disk, you're thinking of spinning this little wedge or thingamajig around the x-axis really quick. If you ever saw a lathe or something like that, it's that process. What happens is you have this disk figure resulting. Okay, so if I took this thing and spun it really quick, I would end up with, maybe not there, but I would end up with this thing. And I'm just spinning this one guy here. Crud, I did it again. So if I spun that, I would end up with this kind of object. Okay. Where the little rectangle is sitting right here, okay, inside the disk. So in order to kind of figure out the volume of the the figure that's being traced out by revolving the region around this x-axis, what you do now is figure out the volume of this particular disk created by revolving this one little wedge around the x-axis, and then you'll add up all of the disks to get an approximation for the volume of this figure. So if you were to spin this around the x-axis, and that's what we're looking for the volume of that thing being spun. If you were to spin that around, you would get kind of a vase-looking object. It would kind of look like, let's see if I can kind of draw it. It's kind of like this, you know. That kind of looking at. We're looking for the volume of this. You're looking for the volume of the area under the curve f of x as we rotate that region about the x-axis. Okay? And how we're going to do that, we're going to figure out the volume of all these little disks inside of here and then add them up. So just like before, we had area elements. Now we're going to have volume elements. So in particular, if you take this disk and kind of lay it flat, you can put it in terms of f of x and change in x and figure out the volume for it. Because we know the volume of this is basically just a flattened cylinder. Note the volume of a cylinder, what was that? It's 2 pi r h. Right? So we could figure out the volume of this particular slab. Let's take a look. Well, the height is just going to be this dimension, which is going to be change in x, right? From this. The width of the base is changed in x, and that's what this dimension is, this dimension right here. That's this. If you're to kind of transpose it and put it over here, the change in x is now going to be the height. Then the radius, this distance here, if we go back to the picture, the radius going from here to here, well, that's just f of x sub I. Okay, so that's f of x sub I. And then we can figure out the volume of that particular cylinder. Well, that's just 2 pi, or sorry, it's pi r squared h. Sorry, pi r squared h. So it's pi times r, and r is f of x sub I squared, and then times the height, but the height is just change in x. So to get an approximation for the volume of this region being rotated about the x-axis, you just add up all these v sub i's. So the volume then is approximately the sum of these pi f of x sub I squares change in x's. Okay, and I just ran out of ink on top of all my other issues. Okay. Alrighty then. So the picture that you're kind of finding the volume of, let me try to draw that really quick here. So here's the original picture with all the rectangles. I'm going from A to B, and I'm splitting up into a bunch of little rectangles. Okay. I'm revolving those rectangles to create this vase-looking thing, and so what does that look like? It'll look like this. See how quickly I can draw this. You know, it gets smaller and smaller in the middle, and then it starts getting bigger as we go out towards A. Okay. But what you're doing is finding the volumes of all those little parts there, and now it's in 3 dimensions, of course. So, you know, we approximate the volume of this object by adding up the volumes of the little disks, basically. And then at the end of the day, we'll take the limit of this thing as the number of disks goes to infinity, right? So it's the limit of the sum from I equals 1 to n of the v sub I will give you then at the end of the day the integral, right? So it would be pi times the integral of f of x squared dx. And in the integral, you could see the remnants of the formula for the volume of a cylinder, pi r squared h. Okay. And that was true even with our usual Riemann sum, where we're summing up all of the areas. When we took the limit, then you get the integral of f of x dx, which is basically just height times base, base times height. So the geometry is kind of encoded in the integral. Okay, so let's take a look at some of these problems. So this is going to be basically the workhorse for this section, that particular integral there. Problem 1, we want to rotate then this given region about the x-axis. And of course later we'll be rotating about different axes. And so rotate the region about the x-axis. The region is given as y equals negative x plus 1. So it's the region between this curve and the x-axis and the vertical line, x equals 0. So negative x plus 1, its y-intersect is at 1. It goes down 1 over 1. So we should have this curve here. I want to find the volume of this region rotated about the x-axis. I like to do little rectangles to kind of remind me about how this thing is working. I also remind myself which axis I'm rotating about. At the end of the day, you don't have to draw these pictures. At the end of the day, the object is going to be kind of a cone-shaped character like this. Okay, and what else? I get a radius function. So it says pi f of x squared, but if you remember what f of x represented in this context, it represents the radius of your particular cylinder. So it's this height f of x here, which becomes the radius of this particular disk. Okay, so the f of x, remember, is the radius. So when you're doing these problems, identify your radius to put in there. So I'll just say this is a radius function, r of x, and the height here is given by this formula here. So negative x plus 1 will give me the radius function for this object. Okay, and then everything else is pretty much just plug and chug. You go pi integral, we're integrating, we're accumulating these disks from 0 to 1. So 0 to 1, and then we have negative x plus 1 squared dx. Okay, and then we can integrate that, of course. So I get pi integral, I have the FOIL, so x squared minus 2x plus 1 dx. And then that'll be pi times x cubed all over 3 minus 2x squared over 2 is x squared plus x. And then I'm going from 0 to 1. That'll be 1 pi times 1/3 minus 1, which is 3/3, plus 3/3. So it's just pi over 3. Right? I'll make sure, yeah, it's pi over 3. Okay, let's try another. This is 11. I want to rotate the region in between square root x, y equals 0, and x equals 3. So first I'm going to get a graph of that region. So here's my square root x function. Y equals 0 is, sorry, the x-axis, and then x equals 3 is 1, 2, 3 is right here. So this is the region I'm rotating. I'm going about the x-axis. The rectangle in this case is right here. Okay, so my radius function, if you wish, the height of this rectangle is given by this formula here, y equals square root x. Okay, so for any given x value, I can figure out the height or the radius by plugging that x value into this formula. At the end of the day, when I rotate this, I'll get kind of this, this shape. Okay. And let's make it happen, right? So I'm going the integral, it's pi r squared basically, so square root x squared dx, and I'm adding up disks from 0 to 3. Okay, so this will just become pi times the integral of x dx, so pi times x squared over 2 from 0 to 3. Plugging in 3, you get 9/2 pi for the volume. Okay, you can rotate about different axes, obviously, not just the x, but also the y-axis. You're going to get different sort of shapes. The one helper bit of information is that these rectangles, you kind of want to know where their bases are located. So when I'm accumulating these rectangles, their bases are on the x-axis. So the formula for the radii will be in terms of x. If you're going around the y-axis, the rectangles will be oriented horizontally. So the bases will be on the y-axis, and your radius function will be terms in y. Okay, so horizontal versus vertical revolutions. Okay, so for let's say we have this kind of shape here, like a circle, and we're rotating in this region, in this direction around the x-axis. Your rectangle will be based off of the x-axis. So your radius function will be in terms of x. Okay? Your integral then pi, let's say this is 0 and this is a, will go from 0 to a of whatever your function is. Let's say it's f of x. Your radius function, r of x, dx. Okay? And then if you're revolving around the other axis, you'll have to solve for this function in terms of y, so you get some g of y. Your radius function now, of course, is r of y, which is, in this case, g of y. But your rectangles will be oriented horizontally, like this. Okay? So you're revolving around this axis now. And then your cylinder or your discs will kind of look like this. Okay, so over here the discs oriented in this direction. Okay. And the formula here, pi integral from, let's say, 0 to b of some other radius function, r of y, and it will be with respect to y. Okay. So the accumulation is in this direction for that graph, and this for this graph, the accumulation goes in this direction. Okay. Okay, so maybe let's try some. Let's try number 9. So y equals x to the 2/3 power. The book was nice enough to graph it and tell what region we're interested in. Okay, so in this particular case, I'm going to desire this region. I'm rotating it about the y-axis this time, and I need to figure out what that is. So the end object that I'm after is this trumpet figure, so I need the volume of that figure. And the radius function should be in terms of y. Okay, so my rectangles will be oriented horizontally. With this red rectangle here is my guy. So given a particular y, I need to know this distance, and that would be given by this kind of, but I need to solve for x. Okay, so if I raise both sides to the 3/2 power, I get x equals y to the 3/2. So that gives me the formula for my radius. And then I'm accumulating from 0 to 1. Okay, so my running man is going in this direction, adding up the rectangles like that. So my integral will be pi times r squared, so y to the 3/2 squared from 0 to 1 dy. Okay, so that's quite easy. Multiplying out these two exponents, you get y to the 3rd dy, which of course is pi times y to the 4th over 4, evaluate from 0 to 1, so you get pi over 4. A little bit harder then will be non-axis revolutions. So section 3, non-axis revolution. And the way you do this is just to adjust your radius function accordingly. So adjust r of x accordingly, or r of y accordingly. Okay. So in particular, we'll look at example 2, where we want to rotate this kind of football region. So rotate the region bounded by y equals 2 minus x squared, y equals 1. So the region bounded by these two graphs. And we're rotating it about the line, rotated it about the line, y equals 1. So first I want to graph the stuff. 2 minus x squared is a parabola, basically shifted up 2 places and then rotated upside down. So I get this picture. The line y equals 1 is a horizontal line right here. And that's also the line we're rotating about. Okay? So the little rectangles that I'm adding up will be right here. The end picture is going to have a hole in it, right? It's going to look like a football with a hole drilled through the center of it. Okay. Whoops, no, it's not. It's just going to look like a closed. I thought we were going around the x-axis. Sorry. If we just go around the line y equals 1, it's just going to look like a Stewie head, right? It'll look like this. Okay, so I don't have to worry too much, but the radius function I'm going to have to worry about a bit. So r of x is going to be the difference of two particular rectangles. So if you note, this distance right here is the difference of this rectangle, which has a distance of going from here to the top of this graph here. So the length of this rectangle, if you know a particular x value, is just going to be 2 minus x squared. So the blue rectangle has length 2 minus x squared. I just need this red rectangle length. So what you're going to need to do is subtract away then this other rectangle, which goes from here to the line y equals 1. I'll try to put it in yellow, I'll put it in green. Okay. Running out of colors. So it's this blue rectangle minus this green rectangle. And the height of the green rectangle is a constant. It's always 1, right? So it'll be the 2 minus x squared minus the height of this, this other rectangle, which is 1. Okay, so at the end of the day, when all is said and done, our radius now is 2 minus x squared minus 1, which is equal to 1 minus x squared. So you re-envision sort of this height as a difference between known heights, the height to the parabola minus the height of this line that you're kind of taking away. This minus this gives you the red distance, this distance here, which is this distance. So it's this to here, here to here, and then minus here to here. Okay, so at the end of the day, then we'll have pi times r squared, which is 1 minus x squared dx. Okay? And we're integrating from this point to this point, which is just where these two graphs intersect. So I need to figure that out as well for the integral. So I need to figure out where is 2 minus x squared equal to 1. So I can solve that pretty easy. That's where x squared is equal to 1. That tells me x is plus or minus 1. So I can go from -1 to 1 and evaluate that integral. I'm going to spare us the details. It'll be 16/15 pi. Okay. Okay, so that's that idea. Just think in terms of differences is the way to get it done for the radius. All right, the next section is the washer method, and this is for when you're rotate, like in this example, I thought maybe there was a hole in the object. When you have holes in objects, you have to use a washer method, or in the next section, you can use a shell method, which is usually a little easier for these. But for right now, we introduce the washer method. And you're going to need two radius functions, big R of x and little r of x. So first, how does this work? And we go back to, again, our thinking of this integral as an accumulation of rectangles, in this case, accumulating volumes of objects. And let's consider then now two graphs. So we have, on some interval from a to b, we have a function f of x, and then just the equation of a horizontal line to make things easier, g of x. Okay, so again, you could section it up into a bunch of little rectangles, and then consider a particular rectangle here at x of I. The width of this rectangle, we'll say, is change in x. And then we're rotating again about the line, about the x-axis. And the object that will be sort of traced out will now be a washer. So just for this one particular rectangle, what will it look like? It'll look like this. So you get this washer object being traced out. Right. So now in 3 dimensions, we get this thing, and the rectangle in this object, where is it located? It's right here. Okay. Okay, so to find the volume of this object, which has a hole through the middle of it, when you spin it around, you have to sum up the volume of these objects. So to figure out the volume of this object, again, it's just a matter of kind of remembering your basic geometry and how all that stuff works. We want to put it in terms of f of x and change in x. Okay, so first off, we know that this distance here, the height, is change in x, and then to get the volume, or to get the the overall volume of this washer thingamajig, you're going to need to take a difference of two discs or two cylinders. So v sub I will equal the difference. So you'll have the sort of the donut hole, which its width here, or its radius here, is based off of the g of x. So this distance is g of x sub I. And then you worry about the outer one. So the f of x sub I is this distance here. Okay. So I should try to smoosh it in there. It's to right there. Okay. So v of x of I will be the volume of the bigger disk, which is pi times, of course, r squared, which will be f of x of I squared times h, minus the volume of the inner disk, which is pi times g of x sub I squared times change in x. And then we could rewrite that by doing some factoring. We just have pi times f of x sub I squared minus g of x sub I squared times change in x at the end of the day. So when you sum all these up and you take your limit, you end up with our integral du jour, limit of the sum of the v sub I as the number of washers goes to infinity will equal pi times the integral of the big radius, so we can call it r of x squared, minus the little radius, which we'll call r of x, little r of x squared dx, from wherever you start to wherever you end. So that will be our formula. In this case, this big R of x was f of x, and the little r of x was g of x. Okay, okie dokie. So anyways, let's continue on and look at some examples. In particular, number 13, we'll look at. So number 13, we're given y is x squared, and then y is 4x minus x squared. Okay. I want to graph these guys. This guy is just a parabola centered at the origin. This guy's a little bit different, right? We can find the x-intercepts. Let y equals 0. Let's factor. So the x-intercept's at 0 and then 4. And then its vertex, you can find just by taking the derivative and setting it equal to 0, right? Negative 2x plus 4 is 0. So negative 2x is negative 4, so x is 2. And then the corresponding y coordinate will, of course, be 8 minus 4, which is 4. So at 2, 4, it has its vertex. The intersection points set these equal to each other. You have x squared equals 4x minus x squared. Okay, so move the x squared over either way. 2x squared minus 4x is 0. Factor out the 2x, you get x minus 2 is 0. So either x is 0 or x is 2. Okay, so we get a pretty good picture there then. X-intercepts at 0, 1, 2, 3, 4. The x-intercepts of this thing are at 0 and 4. The vertex of this thing is at 2, 4. And 2, 4. Its shape is like this. Okay. And then this thing is just concave up, and it's going like this. Okay. And we want to rotate this object about the x-axis in part A of this question. Okay. So identify your rectangle, the thing that's being rotated out, and that'll be this guy right here. Notice this rectangle is perpendicular to the x-axis. What does that mean? That means we need our radius functions to be in terms of x. Okay? So our big radius is the distance from here to the top of the rectangle. So maybe let's put that in blue. The big radius is this distance. Okay? So r of x is going to be from here to here. Here to here is given by this parabola. Okay, so that would be 4x minus x squared. And then let's put the smaller one in green again, so little r of x. That rectangle is given from here to here, here to here. Okay, so this rectangle right here gives you little r of x, and that height is given by the other formula, y equals x squared. So then at the end of the day, our integral, and we know the intersections, so it's going from 0 to 2, and we need a pi there. it'll be big R of x squared. So we'll have 4x minus x squared squared minus little r of x squared dx. Okay. And we'll just leave it at that. A lot of the questions on the first test, what I'll be getting at is just the setup. Okay, so like the first 10 questions, I just want you to set up the integral. And then the next like 5 or 6 questions, I'll have you do some evaluations just so you get practice doing integrals. So in your homework, your first step, set up the integral. Okay, check it on Calc Chat, make sure it's set up correctly, and then get some practice doing the integral. Okay, so at least here, the most important step, in my opinion, because I think you already know how to integrate to a certain extent, is just how do I set up the integral. Okay. Okay. Let's look at non-axis rotations with washers. So this is section 5 now. Non-axis rotations. And this is a washer method type deal. Look at the same problem, so number 13, but now we'll rotate about a different axis. Y equals x squared, and then y equals 4x minus x squared. We want to rotate, and the part B of this problem, rotate about the line y equals 6. Okay. So what you're going to have to do is adjust your formulas for your radii. All right. So again, what does the picture look like? It looks like this. Okay. Now we're rotating about the line y equals 6. Okay, so that's this line here. Our rectangle will be perpendicular to the axis of rotation. So maybe I should write that down somewhere. Rectangles should be perpendicular to the axis of rotation. And wherever the base of the rectangle is, that's your variable. Okay, so anyways, in this case, the rectangle will look like this. Okay. And it's perpendicular to this axis right here, which is what we're rotating about. So there's a huge hole in this thing, and the end object is kind of like a, I don't know, it's kind of like a cone with a bunch of junk torn out of the inside of it. Okay. Anyways, I need formulas for r of x and little r of x. And so big R of x is going to be the distance from here to here. Okay. And then little r of x is going to be the distance from y equals 6. Let me extend this a little in case I need to do some more work here. Little r of x is this distance here. Okay. So little r of x is going to be in green here. So I need to find formulas for this blue rectangle, the distance from here to here, and then also a formula for the distance from here to here. Okay, okay, so for the first one, this blue rectangle, I can think of it as a difference of, so what it's this, so I need the difference between this and this, which is this distance, and then just subtract away the distance from here to here. So minus this distance. Okay. So big R of x is going to be this distance, which is 6, minus then this littler distance, which is given by this curve here, which is y equals x squared. Then for the green guy, again, I can think in terms of differences, right? So this green guy will be the difference between this rectangle all the way from here to here, and then this rectangle, right? So to get the distance from here to here, I take this distance and subtract away this distance. I take this distance and subtract away this distance. It's this distance minus this distance, right? So the bigger distance, again, is 6. So for the little radius, the big distance is 6, and then I'm subtracting away this height, which is given by this formula. So minus 4x minus x squared. So when all is said and done, then my integral will be just a monster of an integral. So again, what I'm saying is make sure you got it set up right, and then worry about integrating. So it'll be pi times the integral from 0 to 2. So I'm adding up all of the volumes of the washers from 0 to 2, and it's going to be 6 minus x squared. Yeah, crap. So it would be, anyways, pi times the integral from 0 to 2 of 6 minus x squared squared minus little r of x squared. So 6 minus 4x minus x squared, all of that squared, dx. Okay. I'll leave the details to you, but that's pretty much the idea. Okay, so these get a little bit more complicated when you're trying to figure out the two radii. But as long as you think of it in terms of differences of rectangles, I think you'll be okay. All right. Okie dokie, that'll do it for this section. Thanks for watching.